Hey everyone, welcome to another day of calculus. Today we are going to talk about definite integrals and the fundamental theorem of calculus, part 1. Now, last week we talked about indefinite integrals. Indefinite integrals are just pretty much the process of taking the antiderivative, right? And so we would take the antiderivative of some function, let's just call it x squared, and dx, that's a really ugly d, but sorry, dx, and so we'd end up with x cubed over 3, and we'd have our plus c value. That's an indefinite integral, just some sort of equation that we get after taking the antiderivative. Well, now, the definite integral is pretty much the process that we could actually find the actual area under the curve. Because notice how now we have these a and b values. So this is called my lower limit and my upper limit of the function. And pretty much those limits are basically telling us that if I have some sort of function that I want to find the area of the curve under, I'm starting here at A, I'm ending here at B, so the upper and lower limit are telling me what interval that I'm looking at of x values. So I start at A, I end at B, and so that tells me that I'm just looking to find this specific area under the curve. And so now, utilizing our fundamental theorem of calculus part 1, which I'll show you in a moment, we are going to be able to find that exact area. Right. Now, the process for this is going to take a couple extra steps from just taking the antiderivative. We've got a few extra steps after that, but overall, not a bad process. Now, normally when we take the antiderivative of f of x, we write the new function as capital F of x. All right, so normally, again, if we have an initial function and we take the derivative, we write it as f prime. And so if we take the antiderivative of f prime, it goes back to f of x. But here, if I'm starting with f of x and I take the antiderivative, what does that give me? We haven't had a notation for that yet. Well, we call that now capital F of x. So it's kind of like the derivative of capital F would give us little f, the derivative of little f would give us f prime, but the antiderivative would go back in the opposite direction. So if this a and b value weren't here, the antiderivative of f of x, little f of x, would be capital F of x plus c. That's the indefinite integral process that we have been doing last week. But now, because we do have an a and b value, when we take the antiderivative and get capital F of x, we're going to write this vertical line here and write a and b. That vertical line pretty much just means I'm going to evaluate at, or from, evaluate from. So I'm going to evaluate over this interval of A to B. All right, so that's pretty much what that vertical line is telling us. We're going to evaluate that overall interval. And then what we're actually doing is we are going to evaluate f of b minus f of a. So we're going to plug both b and a into our antiderivative function. We're going to do the higher limit minus the lower limit, and whatever that value comes out to be afterwards, that is the area under the curve. And that it would be our final answer to the problem. So let's go through an example and see how we do. All right, so here's our first example. We've got the antiderivative from 1 to 3 of x squared dx. Now, again, the first thing that we should notice here is that we have this upper and lower limit of 1 to 3. Okay, if we did not have that upper and lower limit, we would just be doing the process that we did last time, x cubed over 3, and we have a plus c. Whoops, I meant if we did not have the a and b value. Right, then this would be, oops, I'm still on the eraser. I meant to go back to the marker. Let's start that over, x cubed over 3. Right, and that would be our answer if I did not have that a and b value to start. Well, now I do have an a and b value though. So I start out the same way that I did for the indefinite integral. Okay, we first have to take the antiderivative of the function. We're using our power rule. So we add 1 to the exponent and divide by the new exponent. Now, because I have that a and b value, I no longer need the plus c, right? Instead of the plus c, we're going to go straight to this vertical line, saying I'm now going to evaluate this function on that interval that I'm given. That interval is from x equals 1 to x equals 3. So next thing we do is we are going to evaluate f of the higher limit minus f of the lower limit. So what I have to do is I pretty much have to plug 3 into my x cubed plus 3. So that would be 3 cubed over 3. Minus, I need to plug in 1 into my function. So it would be 1 cubed over 3. And I simply have to simplify this to get the final answer for the area under the curve. So 3 cubed, hopefully all of you guys can remember that. 3 cubed is 3 times 3, which is 9, times another 3, which is 27. Minus 1 cubed is 1. All right. Now 27 divided by 3, yes, I could simplify it to 9. However, I don't want to have to do 9 minus a third. That's kind of a little weird. So I'm going to leave this as in fractional form. So 27 thirds minus 1 third is going to be 26 thirds. And that is my answer. That is the area under the curve of this function. So that function x cubed, the function x squared, right, which normally our x squared is just a parabola. So if I were to start at 1 and end at 3 on that function, this area under the curve here would be an area of 26 thirds. And that's it. That's our process. That is our fundamental theorem of calculus part 1. Let's do another example. All right, so now I've got a little bit more of a polynomial. But again, first thing I notice is that I have this a and b value, so I'm not going to have a plus c. So there's not going to be a plus c, no plus c, because I have my a and b. All right, so you either need your a and b or you need your plus c. You cannot have both. So in this case, because we have our a and b, we have no c. So step 1, take the antiderivative x squared. The antiderivative of x squared is x cubed over 3. Minus the antiderivative of 3 is going to be 3x. Again, because we have our a and b, there's no c value. But we are going to evaluate from 1 to 2. That is the interval that we were given. So that interval means that I'm now going to have to evaluate f of 2 minus f of 1. So now we have to be a little bit more careful because I don't have one term anymore for my function. I have 2 terms. So I have to plug 2 into the x cubed over 3, but I also have to plug the 2 in to the 3x. So both functions need 2 plugged in. So now I'm going to do the same thing with 1. So I have my x cubed plus 3, so that's going to be 1 cubed over 3, minus 3x, so it's going to be minus 3 times 1. And I have to simplify both of these parts. All right, so let's start over on the left. 2 cubed, 2 times 2 is 4, times another 2 is 8 thirds, minus 6. And then I've got this subtraction, and I'm going to have 1/3 minus 3. So I've got the left side and the right side. Okay, so now we have to simplify this a little bit more. I'm kind of running out of room here. I'm going to erase this a little bit and come all the way up to this top right side. Okay, so I've got 8 thirds minus 6 minus 1/3 minus 3. Okay, so what I'm going to do is I'm actually going to distribute this negative sign across so I can get rid of my parentheses. So I've got 8 thirds minus 6. I am negating 1/3, so that's minus 1/3, and now I'm negating negative 3, so that becomes positive 3. So now I've got a little bit more of, I can combine some common terms. So I've got 8/3 and -1/3. So 8 and -1 becomes 7/3. And I've got a -6 and a +3. -6 and +3 is -3. And we still have to combine a little bit, so I'm going to get a common denominator here with my 3. So I'm going to multiply this by 3/3. So that now gives me 7/3 on the left side and 9/3 on the right side. Again, 9/3 would simplify back to just that original 3. So they are equivalent. So 7 minus 9, we, simplify the numerator. 7 minus 9 is -2/3. And that is my final answer. That is my area under the curve. For the function x squared minus 3, if I was only looking from x equals 1 to x equals 2. Okay. Again, if I was trying to draw a little picture for that, x squared minus 3 would be a parabola that is shifted down by 3. And if I was looking at the function from 1 to 2, I'm looking at this area here. Now, some of you might be like, wait, we didn't deal with any areas that are negative. How can an area be negative? Right? In geometry, we were always told that you can't have a negative area. Well, the difference here is that when we're dealing with definite integrals, that negative sign takes into account the fact that this area is below the x-axis. So if your area is below the x-axis, that's going to be a negative amount. And if your area is above the x-axis, so let's say I was dealing with this area up here, that area would be a positive amount. So your areas are going to be positive or negative depending on whether they are below the x-axis or above the x-axis. Something that we're going to talk about more in future lessons. All right, we got one more example here. And this final example goes back to one of those polynomial tricks that we talked about in a lesson from last week. So really the first thing we want to do here when I see 2x minus 1 squared is I'm going to rewrite this as 2x minus 1 times 2x minus 1 and do a little FOIL. So 2x times 2x is 4x squared, negative 2x and negative 2x, and then finally negative 1 times negative 1 is positive 1. So I'm going to come over here to the left-hand side just to save some room. So that means that I have 4x squared, negative 2x and negative 2x is negative 4x plus 1. So I'm really taking the antiderivative of this polynomial, and that is equivalent to my original 2x minus 1 squared. Those two things are equivalent. Okay, so let's take the antiderivative of each term. So coefficient of 4 stays, x squared is going to become x cubed over 3. Minus coefficient of 4 stays, x is going to become x squared over 2. And then the antiderivative of 1 is x. So this entire polynomial is going to be evaluated from -1 to +1. So this is going to be the one that has the most terms. Because when I do f of 1 minus f of -1, I'm going to have 3 terms for both of these. Okay, so on the left-hand side, I have 4x cubed over 3. So that's going to be 4 times 1 cubed over 3 minus 4 times 1 squared over 2 plus 1. And then on the right-hand side, I'm going to have 4 times -1 cubed over 3 minus 4 times -1 squared over 2 plus -1. Oh, that was a little messy. Plus -1. All right, I would say for this problem, if you have a calculator and you want to use that to help you out, that's fine, no worries. Take a moment right now, though, see if you can simplify this down to one term, okay, and see what you get, and then we will come back in a moment to see how you did and look at my answer. All right, so final answer is 14/3. Now, as you can see, there's a lot of algebra to go through here by hand. Again, if you want to use a calculator to help you out, no problem. But just kind of recapping. All right, 1 cubed is 1 times 4 is 4. 1 squared is 1 times 4 is 4, and that 1 stays the same. This 4 over 2 can just simplify to 2. And this negative 2 and this positive 1 can simplify to negative 1. So I've got 4/3 minus 1 for this simplification over here. Now, with the negative 1, all right, negative 1 cubed is negative 1. Times 4 is this negative 4. Negative 1 squared is positive 1. Times 4 is 4. Again, this 4 over 2 can simplify down to just 2. And this negative 2 and negative 1 becomes negative 3. So that's where we get the negative 4/3 minus 3. Now at this point, I distributed the negative sign across to get rid of my parentheses. So we have our 4/3 minus 1 from the left, and now we get positive 4/3 plus 3 on the right. So 4/3 and 4/3 becomes our 8/3 over here. And the negative 1 and the positive 3 become 2. Now I need to get a common denominator here in order to simplify this. So the common denominator would be 3. So I have to multiply this side by 3 over 3. And so that's where I get my 6/3 from. And 8/3 plus 6/3 leaves me with 14/3. So that definitely was the trickiest one, the one with the most algebra. But again, like I said, if you want to use a calculator just to kind of help you out with that algebra, that's fine, no worries. Hopefully everybody was able to get 14/3. If you're using a calculator, though, they might give you that answer as a decimal, which is probably not the best because then it will be an irrational number. But 14/3 is equivalent to 4 2/3, or that would show up to be 4.666 repeating. You really should not write 4.6 or 4.7, right? You shouldn't round any of these things. So if your calculator gives it to you as the decimal, you really should have that the bar above the number. To signify that it is a repeating number, an irrational number. Okay. All right. So the next slide here. These are the 3 problems that I want you to do for homework. So on the same sheet that you were writing these notes, please now just write down homework problems, and I would like you to, on the same sheet, fill these out, and you are going to take a picture and submit them all together on your Google Classroom page. So again, take a moment to jot these all down, pause the video if you need, and let me know if you have any questions. All right, have a good one, guys.